Hello, welcome to AP Physics C, video number 1. Today we're going to be talking about one-dimensional kinematics. And we're going to start by talking about position. Position is the location of an object with respect to the origin of a coordinate system. The coordinate system depends on the problem and the scenario. And based on your coordinate system, that position can be positive or negative. Motion is the changing of an object's position over some period of time. Very similar to position is this idea of displacement. Displacement is the change in an object's position from where it started to where it currently is. This is different from position in the sense that position just refers to where something is in some reference frame. Displacement identifies where something is compared to where from some starting point. And we look at position in terms of x. We can say that change in position, delta x, or the change in x, is x minus the initial x. Notice that in the APC curriculum we do not say the final position minus the initial position. All final values are just given with the variables without the subscript. In addition to x being the position symbol, r is also sometimes used, especially in rotational motion and gravitation. So any radial displacement, how far two centers are away from each other, is given by the symbol r instead of x. Similar to displacement is the idea of distance. Distance is the length traveled during motion. The difference between distance and displacement is that distance does not depend on direction. It always has some positive value, and the idea here is that the difference between where you are and where you started is not always the same as the path you took, unless it was a straight line. So distance captures this idea of how far it's been moved over the course of its path, whereas displacement just cares about where you started to where you finished. The second idea in kinematics that we're going to talk about is velocity. Velocity is the rate at which displacement undergoes over a period of time. And we're going to start talking about it in terms of average velocity. So if we're looking at average velocity, it's delta x, or change in our position, divided by delta t, which is the change in our time. So we have a change in position over a change in time, and that is how we refer to our average velocity. If you're looking at this graphically, you could find the average velocity by taking the slope of a secant line on a position as a function of time graph, which you see below. Here we have position plotted on our y-axis and time plotted on our x-axis, and we have a graph showing where the position is as time varies. If you want to know what the average velocity is between 2 points, say time initial and time final, you would end up just taking the slope of this line and again that corresponds very nicely with our equation where we have change in x over change in time. When we're looking at velocity, average velocity is not going to represent any particular velocity on our path. However, if we were to take the time period and shrink the time period small enough, and here we have a large time period that you see on the screen, if I shrink the time so that way my initial time and my final time get progressively closer together, you'll see that the secant line that's developed starts to approach a point, and when we get to that point where the change in time approaches 0 or a nil value, our change in x still has some value, and as those two values approach 0, the average velocity approaches what we would refer to as our instantaneous velocity. And instantaneous velocity is the rate of change in displacement an object undergoes at an instant of time. So as an object is moving, undergoing motion, the velocity that it's moving with from moment to moment may change, may stay the same. Instantaneous velocity is this idea of what it is at that time period. If we're looking at this in terms of calculus, we could say that the velocity is the time derivative of the position value. So here we have the limit as time goes to 0 of delta x delta t, meaning that time is going to 0, is the same way of saying that we're taking the derivative of x with respect to t. So those two values really refer to the same mathematical operation here, and that's how we look at instantaneous velocity. Let's do an example of this. So here we have a function of x, and this is right out of your reference table. It's a very familiar equation to you. It's saying that the position of an object is equal to where its position starting was. So x equals x sub 0. That's its initial position. So where we are currently is where we started from, plus our initial velocity times time, minus 1/2 9.81 times t squared. So this would be the position of something, per se, for example, that might be falling. If we're looking at the velocity, we want a function of velocity. We would say that velocity is the derivative of x with respect to t. And so if we take the derivative here with respect to x, we're going to apply this to each term individually. The initial position is a constant. Derivative of any constant is 0. We have the second term, which is velocity initial times time. We're taking the derivative with respect to time. So time goes away, we just have initial velocity, and then we have 1/2 9.81 t squared. We drop the 2 down, 1/2 times 2 is 1. So we end up with velocity equals whatever our initial velocity minus 9.8 t. And this makes sense. This is the function that would describe an object that's falling in free fall, and that should be familiar to us all. If we're looking at acceleration, acceleration is the rate of change in velocity an object undergoes in an instant of time. So very similar to instantaneous velocity, we have instantaneous acceleration at that instant in time. How much is our velocity changing? And we can look at acceleration as the first time derivative of velocity. We could also look at acceleration as the second time derivative of position. So mathematically we could identify these relationships as such. And if we look at an example of this, in this example it says the position of an experimental rocket moving along a long rail is measured by the function x equals 5t plus 8t squared plus 4t cubed minus 1/4 t to the 4th, or the first 10 seconds of the motion. What's the velocity and acceleration of the particle as a function of time? So we have a function of position here, and what they're asking us for is not some numerical answer, but rather they want us to write functions that represent the velocity over this 10 seconds and its acceleration over its 10 seconds. So if we're looking at the velocity, velocity is the first time derivative of position, and if we take that and we apply our power rule across it, 5t becomes 5, 16t, that's 8 times 2. We have the 12t squared, that's 4 times 3. Remember that's it's n to the minus 1. And then 1/4 t squared goes to a negative t cubed. So all we've done here is we've applied the power rule to each term individually to find a function of velocity. Now this function will tell us the velocity at any moment in time as we go along. If we did the same thing to acceleration, now we're going to take the time derivative of velocity function that we just found, which is the same as taking the second derivative of the position function, and we apply the same thing. The 5 goes to 0, 16t goes to 16, 12t squared goes to 24t, and a negative t cubed goes to a negative 3t squared. So here we've taken a function of position and we've determined velocity functions as well as acceleration function over this time period. And this is a process that you will go through time and time again in this class over many different units, going time derivatives to find higher values. The last thing we're going to talk about in terms of acceleration is constant acceleration. If we're using calculus in this respect, we're not going to be talking about constant acceleration, but there are scenarios where acceleration is constant. In these scenarios, we have a set of equations that we can use. I'll refer to them as the kinematic equations. that can be used to solve these constant acceleration problems. The first one, and these are all in your reference tables, is velocity equals velocity initial plus acceleration times time. That would be a constant acceleration. It'll tell us what our final velocity is. Our second one is position equals our initial position plus our initial velocity times time plus 1/2 acceleration times time squared. Please note that while you're applying these equations that you're very cognitive of which way these acceleration and velocities are pointing. If they're adding together or subtracting from each other, you do have to apply vectors to these velocities and accelerations. The last equation is velocity squared equals velocity initial squared plus 2a, and here you see a term x minus xo, that's just saying the displacement. And those three equations can be used in order to find different values for constant acceleration problems. The last thing we're going to talk about today is on free fall. Free fall is any airborne object near the Earth's surface that falls with a constant acceleration of 9.8 meters per second squared directed towards Earth. Free fall is motion due to the gravitational attraction of Earth. We learned last year in Newton's universal gravitation that there's a more sophisticated equation that can be used to determine acceleration at any point in the gravitational field. The 9.8 meters per second squared just refers to the gravitational field at the surface of the Earth, so that's constant there. That acceleration is given a special symbol, and that is the lowercase g. If we're looking at air resistance will decrease the amount of acceleration that's happening. So if you have no air resistance, or if friction or air resistance is negligible, you're at 9.8 meters per second squared. If there is any air resistance whatsoever, and you should assume there is unless you're told otherwise, this will cause the acceleration to decrease in magnitude. In many cases it's not necessary to know exactly what it is, just know that it will decrease the acceleration. The other thing about air resistance you should understand is that the faster an object goes, the more air resistance or the less acceleration that it will feel because of its speed. Let's do an acceleration due to gravity example. In this example, a ball is thrown straight up with a speed of 12 meters per second squared from a window located 10 meters above the ground. How long does it take the ball to reach its maximum height? So here we have initial velocity. We know that we have acceleration due to gravity. We know a height, and we know that when it hits its maximum height at the peak, it'll have a velocity of 0. So here we apply velocity equals velocity initial plus acceleration times time. And since at the peak we're at 0 meters per second, we have our initial velocity, and acceleration is pointing downwards, the object's moving upwards, they can't share a sign, so it's a negative 9.8 t, and solving this for t gives us a time of 1.22 seconds. If we want to know what height the ball achieves, we can use our second kinematics equation, where it's position equals position initial plus velocity times time plus 1/2 at squared. Again, we start at 10 meters above the ground, so that's our initial position. We have our initial velocity and our time. We also have our negative 9.8 meters per second squared as our acceleration and our time as well. So what height does it actually reach? It reaches a height of 17.3 meters. And finally, we want to know what speed does the ball hit the ground with. In this equation that I've just pulled up, the velocity final is equal to the velocity initial plus 2a times the change of position. If we're looking at this, our initial velocity is 12 meters per second, and our acceleration is negative 9.81. Our initial position, say, is 0. That would be what we throw it out of the window at. And then our 10 meters where we land on the ground is below us, so that would be a negative. So here you can see that I've made sure that with my vectors, my acceleration, my position, and my velocity, they all have the right sign depending on which way they're moving. And when we solve this out, we end up with a velocity of 18.4 meters per second. And that should about do it. We will continue these notes in class, and have a good afternoon.